hardware choices shape local AI workflows. The relentless pace of GPU innovation continues to reshape the local AI landscape, with NVIDIA's RTX Pro 4000 Blackwell card sparking debate among practitioners weighing performance, cost, and future-proofing. The 24GB GDDR7 single-slot card, with native support for FP8 and FP4 formats, is pitched as a dense, power-efficient inference workhorse, especially in multi-GPU EPYC server builds. Users highlight that while stacking 4 to 6 of these can yield 96 GB of total VRAM, the realities of PCIe bandwidth, power supply complexity, and the absence of NVLink for fast inter-GPU communication introduce significant bottlenecks for anything beyond straightforward LLM inference. For heavy-duty parallel user loads, think 1,000-plus concurrent requests, the consensus is clear. Invest in high-end SXM GPUs or the Blackwell 6000, which despite a steeper upfront cost, offers better memory bandwidth, simpler system integration, and fewer thermal headaches. Budget-conscious AI builders face tough trade-offs. For a €5,000 local LLM rig, squeezing out maximum VRAM per euro is the top priority to support large models, 30 to 70B parameters, and multiple users. Options include modded 48GB RTX 4090s, waiting for upcoming AMD Radeon Pro R9 700 32GB or Intel B60 48GB cards, or assembling multi-GPU AMD 7900 XTX rigs. Yet software support for AMD and Intel remains uneven, especially for frameworks like Llama or VLLM, where CUDA-powered NVIDIA cards still dominate for reliability and throughput. The advice: check for active support in your preferred stack, and if in doubt, stick with NVIDIA for the smoothest experience. As for running LLMs on CPUs alone, the community is blunt. Even with the fastest EPYC or Xeon chips, GPUs are 10 to 100 DEX faster for matrix-heavy workloads like LLM inference, and the gap widens with scale. For small single-user prototypes, CPUs can suffice, but parallel workloads demand GPUs for any semblance of real-time performance. The memory bandwidth isn't everything mantra holds. Architecture, parallelism, and specialized compute units, tensor cores, MX, matter even more. Advances and trade-offs in LLM compression and security. The drive for efficient, scalable AI brings compressibility, making models smaller or sparser, into sharp focus, but at a potentially steep cost to adversarial robustness. A comprehensive theoretical and empirical study from Imperial College London and collaborators reveals a fundamental tension. Compressing neural networks via pruning or low-rank factorization concentrates the model's attention along a few highly sensitive directions in the representation space. This makes them easier for attackers to fool, even after adversarial training or transfer learning. The researchers provide formal bounds linking neuron-level and spectral low-rank compressibility to increased vulnerability against both EP1 and EP2 adversarial attacks. They show that as compression increases, the model's Lipschitz constant, an indicator of sensitivity to input changes, also grows, amplifying the effect of even small perturbations. Empirical results on standard datasets, CFAR 1000, SVHN, and architectures, FCN, ResNet, VGG, WideResNet, confirm that adversarial robustness drops as compressibility rises, regardless of whether the model was trained with explicit adversarial defenses. Interestingly, the study finds that while unstructured compressibility, e.g. L1 regularization, can sometimes help robustness, structured forms like group sparsity or low rankness consistently introduce vulnerabilities, sometimes even universal adversarial examples that transfer across tasks. The upshot: there's no free lunch in model optimization. Efficient models are not automatically secure, and compression strategies must be carefully balanced against the risk of adversarial attacks. This tension is no longer just academic. Amazon recently suffered a security incident where a hacker exploited a plugin for an AI coding assistant, using stolen credentials to inject malicious instructions, such as deleting files from user machines. The episode underscores the real-world risks when AI-generated code and plugins are not subject to robust security controls, especially as AI code generation tools proliferate in enterprise settings. Local coding, agents, and context management. The ecosystem for local coding agents and LLM-powered tools is in a state of creative chaos. There's no standard setup for a fully local coding agent that continuously improves code bases, though several promising frameworks and workflows are emerging. RuCode, an editor plugin, is gaining traction for its integration with agentic workflows and Model Context Protocol (MCP) servers, enabling more seamless automation of tasks like bug fixing, refactoring, and test generation. However, most users still resort to custom scripts and ad hoc pipelines, often combining open-source tools like Quack, Harbor, All Hands, AutoGPT, and now RuCode, to orchestrate code improvements while maintaining some human oversight. AWS Strands Agents, an open-source SDK, offers a modular approach to building agentic workflows with support for multiple LLM providers, including local models via Llama or LiteLLM. The core loop, goal, plan, tool selection, execution, update, repeat, abstracts away much of the manual orchestration previously handled by frameworks like LangChain or CrewAI. Early community experiments report surprisingly smooth tool routing and output formatting, even for simple weather checking agents, without vendor lock-in. On the model front, Qwen3 Coder 30B-A3B Instruct stands out for local agentic coding, with native support for long context windows, 256K tokens, extendable to 1M, agentic tool calling, and efficient MoE, mixture of experts architecture. It's optimized for repository scale understanding and code generation. The model is compatible with local deployment tools like Llama, LM Studio, and llama.cpp, and supports OpenAI-compatible APIs for easy integration into coding agents. The recommended inference settings, temperature 0.7, top P 0.8, top 20, help balance creativity and determinism. Notably, the model disables thinking mode by default, focusing on direct code output. For those working with modest hardware, e.g. 8GB RAM, 6GB GPU, smaller models like Qwen3 4B in quantized formats, Q4KS, can be run locally, especially with memory-saving features like flash attention and KV caching enabled in Llama. However, users should temper expectations. While such models suffice for simple chatbot or summarization tasks, serious coding or multi-user workloads still demand at least 48GB of VRAM and 128GB RAM. The main use case for small models is experimentation and lightweight prototyping, not production-grade coding assistance. Fine-tuning supervised learning and the RL connection. Community-driven fine-tuning efforts continue to democratize model improvements. For instance, a user's first fine-tune of Gemma 3.4b using the GRPO method, a statistical analysis and lexical diversity rewarding loss, is released as a LoRa adapter, complete with code for others to replicate or extend. This grassroots approach to model customization underscores the accessibility of modern LLM stack. With tools like Unsloth and GGUF, even users with limited hardware can participate in experimentation and sharing. Amid these advances, philosophical debates persist. One thread highlights the increasingly blurry line between supervised fine-tuning on curated data and reinforcement learning, RL. If RL is training on high-ranking outputs, then selecting and training on preferred outputs, whether produced by humans or models, collapses the distinction. Some see this as a trivial observation, others as a sign of paper farming. The reality, as the boundaries between SFT, RLHF, and data curation erode, the best practices will be defined by results rather than taxonomy. Section: LLM agents, plugins, and the limits of automation. The agentic revolution is not without pitfalls. Claude Code, Anthropic's agentic coding platform, illustrates the brittleness of current agent frameworks. Users report that sub-agents, intended to follow custom workflows, sometimes ignore explicitly defined rules, instead inferring behavior from agent names. A workaround, use non-descriptive names, e.g., finder, instead of reviewer, to prevent the platform from injecting its own logic. This semantic leakage points to a deeper challenge. LLM-based agents still struggle with reliably following user-specified constraints, especially when system prompts or naming conventions inadvertently bias the agent. To address the complexity of agent configuration, tools like C-Chook provide a much-needed usability upgrade. By replacing Claude Code's verbose JSON hook configurations with YAML templates, conditional logic, and JQ-powered data extraction, C-Chook makes it easier to automate pre- and post-tool actions, notifications, and environment-specific behaviors. This kind of ergonomic tooling is essential as agentic workflows grow more sophisticated. Meanwhile, the security surface is expanding. The Pwn2Own contest recently noted that contestants are withholding Ollama exploits because of its rapid update cycle and widespread exposure, over 10,000 open servers on the internet. The absence of public attacks should not be mistaken for safety. Rather, it's a sign that attackers are waiting for vulnerabilities to stabilize before striking. Research, retrieval, and local LLM tooling. The local LLM ecosystem is diversifying, with tools like Coexist AI v2.0 offering an open modular research assistant that integrates web, Reddit, YouTube, GitHub, and local file folder search with LLM-powered summarization and automation. The latest release adds vision support, local file chat for PDFs, code, images, smarter retrieval BM25 ranking, and full MCP model context protocol support. It integrates seamlessly with local servers, e.g. LM Studio Ollama, and supports both proprietary and open source models. Coexist AI's design philosophy is clear. Prioritize privacy, local control, and extensibility, eschewing reliance on cloud APIs like Exa or Tavily. For document QA on standard laptops, CPU only, small open-source LLMs like Qwen 3 1.6b and Gemma 3 2b show surprising competence with European languages, notably German and Dutch, in narrow, retrieval-augmented tasks. However, experts caution against overtrusting tiny models for specialized domains like medical research. Even with good retrieval pipelines, it'll still find a way to mess it up. For best results, pair small models with frameworks like Ollama and LangChain and keep expectations realistic. On the TTS text-to-speech front, local quality is rapidly improving. Chatterbox TTS and Koki TTS are community favorites for human-like voices with support for accurate voice cloning. Kokoro Fast API is another option, though its documentation is reportedly challenging. For those willing to tinker, Dockerized deployments make setup manageable, and even CPU-only systems can achieve good results. However, users should avoid cloud APIs like 11 Labs if offline privacy is a priority. Human versus AI context, coding workflows in practice. A nuanced perspective is emerging on the division of context between humans and AI coders. At one end of the spectrum, humans retain all project context, using LLMs as high-level sounding boards, akin to consulting a colleague at another company. At the other, AI agents are delegated entire coding tasks, with humans providing only guardrails. Most workflows fall somewhere in between, using LLMs for code suggestions, targeted bug fixes, or documentation, while humans retain final judgment and context integration. The more context delegated to AI, the less cognitive load for the human, but also less learning and potentially less robust solutions. The key is to calibrate trust and oversight based on the task's criticality and the AI's demonstrated competence. For beginners using models like DeepSeek Coder or LM Studio, the learning curve is steep. Prompt engineering, parameter tuning, temperature, top K, top P, and managing speculative decoding are all crucial for getting useful results. Community advice stresses patience, incremental experimentation, and leveraging Discord channels or forums for troubleshooting. Ultimately, AI coding is a skill in itself, one that requires understanding both the model's strengths and its all-too-human limitations. Beyond AI, open hardware and scene consistency and generation. Not all innovation is purely digital. The dual-screen cyberdeck showcased by Sector 07 exemplifies the hacker ethos. A Raspberry Pi-powered, mechanically refined portable workstation with rotating touchscreens, quick-release PCBs, and attention to ergonomic detail. The open-source design, available on GitHub, serves both as an inspiration for DIY hardware enthusiasts and a reminder that physical interfaces still matter, even in an AI-first world. On the generative AI side, scene-consistent image synthesis is advancing with LoRa models like InScene, designed to generate image variations that preserve background, character, and style consistency. While trained on a relatively small dataset, 394 image pairs from WebVid, the model performs well for most photographic and artistic styles, though it struggles with action-heavy or highly abstract prompts. For best results, users are advised to start prompts with "make a shot in the same scene of," a small but meaningful step toward more controllable and reusable outputs in creative workflows. Speed hacks and rapid LLM response systems. Speed remains a perennial concern, especially for real-time applications. Projects like Blastoff LLM demonstrate a clever architecture. Use a small LLM to generate an immediate prefix, such as a conversational filler, in under 200 milliseconds, then have a larger LLM stream the full substantive response. This prefix streaming approach reduces perceived latency for voice assistants and chatbots, making interactions feel snappier without sacrificing depth. The code is open source and ready to be adapted for custom workflows. As always, the landscape is shifting fast. New tools, models, and vulnerabilities are surfacing weekly. The challenge for practitioners is to cut through the hype, stay evidence-driven, and build systems, hardware and software that are efficient, robust, and above all, trustworthy.